Would you mind telling us the 70 kilohertz bandwidth at 2-1?
Yeah, at 2 to 1. This one is actually, I think this one is closer to 80 and the 40 meter is closer to 70. The return loss is another indicator of the tuning of the antenna. And I believe that concludes what we have here to present on field day. Are there any questions about the slides that I can answer or Greg can answer?
How high do you mount off the ground? What's the takeoff angle? Is that dependent upon how high?
The bottom of the 40 meter loop's about 5 feet off the ground, and it has been usable to make contacts on the CW band.
I just want to make one.
Which orientation, I assume?
What orientation I want to know?
You know, that's one thing we didn't really clearly. We built it.
Like this?
They're sitting like that.
Like what was in the picture?
Yeah.
Then?
Yes.
So they're about the hole.
They're about this far
Yes.
off the ground. You can touch the capacitor when he was tuning.
So you didn't take it and take the central axis of that ring and put that parallel?
No.
Okay. All right.
So the one thing that I want to make sure that everybody knows or does for me is that if you want to be a station captain, I want to know your name tonight, because I'm trying to get the station captains lined up, because you're gonna have to help us build this magnetic loop antenna, because I'm not gonna build 16 of them. Okay, I built 2 of them this last weekend with Brian and Jim, and they were very patient, and we had a great time doing it. But I want to set up another time to build them with you. Jim has a great piece of equipment to test these. So the other thing that's neat about being the station captain is you own that antenna. You can take it home. That 3-foot ring can fit in your attic very easily. So if you want to own your antenna and build it, you need to talk to me tonight, because I want you to come and help me build these antennas.
Build it where? At their location?
We haven't determined that, but Brian is a great shop and stuff like that. So.
And then take it home in my Prius?
Wow. I'll even drive it to your home in my Suburban.
There is a clipboard floating around here where you can sign up, put a maybe on there, it's over here. And so, you know, if you think you might be interested in being involved at some level, check the maybe on there, or actually sign it, right? Yes.
You know, another comment that you got over about harmonics, it's like your
Oh, yeah.
40 meter CW will end up on your 20 meter CW.
Yeah, and 40 ends up on 15. Yeah, that's kind of the way it works. Okay. Okay, so what we have here now is some of the kids from Laterno. Now this is the reason we have 2 of them is because we're recording online. Okay, so this one is the local microphone, and this one is recording on the whoever talking up front. You want to be on? That's it? Oh, okay. No, pass that around. So, talk back. Yeah. Introduce yourself.
All right. Good afternoon, everybody. My name is Adam Lewis, and I'm the team lead of Team 3D RPM. We're a engineering senior design team out of LaTourneau University, which is a university down in Longview, Texas. We were sponsored by Rockwell Collins this year, and we'd just like to tell you a little bit about our project this year. Next slide. All right, so just a little bit about the background. We were told a little bit that the Rockwell Collins Amateur Radio Club put up an antenna on the Rockwell Tower, and that the antenna was not performing as expected, and that they realized that the radiation pattern was mostly radiated north. And so this led a couple of the employees and some people involved with those employees to discuss it and come up with this project as a way of kind of analyzing the pattern of a radiation, I guess of an antenna source. Next slide. So the goals of this project was to utilize multi-rotor drones, or a quadcopter in our case, to autonomously fly a user-defined pattern around an elevated antenna. It would measure the RF signal strength transmitted from the antenna as it's going, and then once it gets back to the ground, that data could be transferred over to a computer, which could then be plotted on Google Earth, so you could analyze it in three-dimensional space, the pattern of strength versus location. And Sarah will talk about the next one.
Hi, I'm Sarah Greenlee. I'm also a member of the team. I'm a senior electrical engineer. This is our mission diagram for our system. What we have is a ground control station on the ground, obviously, and it's at the takeoff place for the quadcopter. So the quad will be given its waypoint file to tell it where to go, and it'll fly around the antenna where we want to take our measurements. And after it completes its path, it'll come back to the ground control station, and we'll take the data from it and analyze it and create a 3D map of our data. Next slide, please. The key features of our project, it will aid the radio industry because right now, for initial troubleshooting for problems with antennas, a lot of times you have to climb the tower yourself, and this will kind of help eliminate that because you'll be able to see exactly what part of the antenna has a problem. Also, it'll enable you to analyze your antenna properties a lot faster because, like I said, you'll be able to see where the antenna radiates, where it's weak and strong, and where its problems are. And we also have a system that has a 3D map for intuitive data analysis. Next slide, please. This is a block diagram of our system. We have our quad here so you can kind of see what's going on. We have a quadcopter, we have the F450 DJI. It has a Pixhawk autopilot with telemetry, RC receiver, and we use a Tyrannus controller to control it when we need to. And we have a ground control station, and that's where we have our flight plans and our 3D mapping. We usually don't have to use the controller in manual mode. That's just kind of a fail-safe thing. We also have a log detector, pre-selector, and receiving antenna mounted on the quad, and that's what we use for the signal string. Next slide, please. This is our current antenna setup that we have right now. We're just using a commercial whip antenna. It's pointed downwards, and it's on a piece of aluminum that's at ground plane. And we tried it without the ground plane for a while, but it had really, really bad dB loss. So we added this to reduce that loss. And you can see from the graph there, our desired frequency is 433.92 megahertz, and the antenna we're using is resonant almost at that point. Next slide, please. And now Ben's going to talk about our log detector system.
Hi, my name is Ben Cayley. I'm also a senior electrical engineer from LaTourneau University. So this is the receiver design that we made with the help of several of the engineers here at Rockwell Collins. It's based on a log detector, which, for anyone who doesn't know, takes in a dB RF input and then outputs a DC voltage that's proportional to the power that's put in. So down at the bottom there, you can see this is our just our main block diagram. It's got a filter which filters it down to 433.92 megahertz, and then it just goes into the log detector and then into our Pixhawk computer, which logs the data. Next slide, please. This is just the output. You can see as power increases, voltage increases. Next slide. And this shows our bandwidth. So you can see it's fairly narrow. I believe the frequency response is about, or the bandwidth is about 680 kilohertz. And that's what it looks like if you run multiple frequencies through a whole system. Next slide. This is a more full block diagram of our system overlaid on the PCB. So we have a front-end filter to kind of get rid of most of the frequencies, a power limiter so we don't kill our circuit, a gain block to provide some isolation, and some SAW filters to provide a more narrow attenuation so we can really get the frequency we're looking for. We have a series of those to ensure we get the right frequencies. And then it goes into a log detector with a buffer amplifier that isolates the output of the log detector from the input of our ADC on our Pixhawk. Next slide. We can skip this one. So next. We can skip this one too, and this one. and this one, and this one. We tried cutting down the presentation a little for tonight. We can get rid of this one too, and skip this one. So this is our PCB in the end. The input is up in the upper right-hand corner, and the signal curves down to the bottom left-hand corner. We tried to avoid curve back so that we didn't get crosstalk across our wires, but due to limited board space, we had to cross back a couple times. However, there still is no crosstalk in our system. Next slide. So this is the PCB that we designed. Next slide. We also have a aluminum box that we purchased to keep RF signals from penetrating our circuit so that we can make sure there's no inerrant RF signals in our power measurements. Now Aiden's going to talk about software.
Okay, my name is Aiden Walter, and I am a senior computer engineer on the team. So in order to kind of explain how the software works, I just want to go through a flow of how we use the system. So the first thing you do is you generate your waypoint file, which is basically a list of points of where the quadcopter will fly to. And you upload it to the quadcopter, and you fly and record data. And then you take that data, and with our program, you can generate a KML file and display that on Google Earth. Next slide. So here is our program. You basically just put in your flight details and your tower details, and you can run your waypoint generator to create your flight plan. And you can also do your KML generator to create your Google Earth file, which plots two separate plots. I'll show this later. Here's an example of the waypoint file. As you can see, that it'll fly around in a circle around the tower. You can't see it from this angle, but it'll fly at different altitudes to get below the point source and above the point source. Next slide. As for the 3D plotting, there's two plots. There's the data plotting, which is just signal strength versus location. And there's the vector plotting, which does some scaling and normalization in order to better show the actual gain characteristics of the antenna. So this is the data plot. So we just plotted the exact signal strength. The colors correspond to the dB level. And then that is exactly how the quad flew around our source. And then these two pictures on the right are vector plots. The top one is without normalization, and the bottom one is with normalization. The purpose of using normalization is to remove the variable of distance out of the equation. So instead of just measuring signal strength according to distance, we are actually trying to calculate the gain characteristic of the antenna at different angles and locations. So this was basically our entire project. We really want to stress how thankful we are for all of our mentors and help from Rockwell Collins at this. If you guys have any questions, feel free to answer them.
Any big issues from the noise from the rotors? Where you've been disconnecting between the license to the receive, just any kind of effects on the motors?
Surprisingly, we actually did not see any noise from the motors. We did a little testing with the spectrum analyzer and really didn't see anything around the motors.
So did you do any testing with data, or did you just do the signal strength? Did you do any, how did you verify the quality of the signal?
Right. We had a handheld spectrum analyzer, so on the ground we walked around with that next to the quadcopter.
How did you normalize your graph?
Oh, how do we
Did you have
normalize the
data? Did you have data? I mean, you're measuring a frequency, and did you measure if there was the right data coming out, or what did you do to calculate?
It was just the signal strength. So we just took out the distance variable. So we didn't actually look into the data.
What are you guys going to do next? Are you going to be entrepreneurs and operating circles? What are you going
to do? We're actually graduating, so this is a one-year project, so like after this semester ends, we kind of give it off to our mentors at Rockwell Collins, and then they can decide, I guess, what to do with it after that.
We really appreciate you bringing the door price tonight. Yeah.
That's a $1,000 raffle ticket for the door price.
How much does the quadcopter cost at the receiver?
The receiver itself, probably about.
The PCB itself was about $500, but we ordered 5 boards, and I think if you were to include the cost of the individual components, probably, I don't know, $650, something like that. But this is for 5 boards. We only used one because we didn't have time to solder on components to all 5 of our boards, and that was just we only needed 1 board, but that was the package that we purchased.
And the quadcopter, how much?
The cost of the quadcopter was
The quadcopter itself was $200. The autopilot was $300, and the Tyrannus was $230.
Nice. How many cuts and jumps on your board?
absolutely none, luckily. We did include some pads on our board in case that we did have to jump some sections, and manage our gain levels. We have several gain blocks which act as some buffers in our circuit, but luckily we didn't have to use any of that. The circuit worked great after it was completed, and which was really surprising, but we were pleased, and so we didn't have to use any of our shortcuts.
Have you documented your design and analysis?
That's the phase we're in right now, actually. This semester still goes on for a few more weeks. So we're currently working on our documentation. We're kind of in the presentation phase right now and documentation phase.
Is that something then